All right, so the Earth has an average density of 5.5. I was mentioning this at the end of the last video, um, and what that means, of course, is that's the average density. So there's stuff that's much less dense than that, like the average rock on the planet. Water is less dense than 5.5, and of course, there's stuff that's more dense, which is, of course, iron, iron and nickel, actually. All right, this is the average value, and it tells us that there is, a good amount of iron and nickel. I know it just says iron here, but it really is iron and nickel that make up the core of the Earth. All right, so let's look at that. So now how do we know? What the Earth is made of. Okay, so or how do we know anything about the interior of the Earth? And the answer is seismic waves. I mean, when we drill down into the Earth, we can't even, it's like 8,000 miles. Okay, to get to here. Let's go back, or let's go back. So to get to the core of the center of the Earth, it's roughly it's 6,400 kilometers, which is roughly 8,000 miles. 8,000 miles, we can barely go 8 miles into the Earth. I mean, we can't even, we can barely get into what's called the mantle of the Earth. All right, so the only way that we can tell what's going on in the interior of the Earth is really these earthquakes. Earthquakes are actually waves. They're of course called seismic waves. All right, and there's different types of them. We're going to explore that a little bit, but they travel throughout the Earth, and they tell us about, by studying them, it tells us about what the interior of the Earth is made of. And the different types of waves travel at different speeds. They do different things, as we're going to see. And anyhow, it allows us to see a picture, right? One of the things that this brings to mind is, when before my kids were born, you go to the doctor and they can do a sonogram and they take a little picture of the baby before the baby's born, and so they're basically using sound waves. Okay, these are different sound waves that propagate through the Earth. All right. So here's an earthquake, and this is a really good picture of what's going on. An earthquake takes place, and there's two waves. Okay, I should use the correct terminology. There are S waves and P waves. P waves are sometimes called primary waves, and S waves are secondary waves. Just call them S and P waves. The way that I always remember this is the S waves. S, of course, can only travel through solid material. S for solid, of course. I mean, they're not solid waves. They're actually called secondary waves. But the S reminds me, hey, they can only go through solids. It's only the P waves that can travel through liquid. All right, now why is that important? All right, so let's say that there's an earthquake that goes off, right here, on the planet Earth. Okay, that earthquake creates very powerful S and P waves. Now we have detectors. I mean, I guess that's what these are supposed to be, detectors. I guess they're people, but or they kind of look like people, but they're detectors all over the planet. We've had them around the planet for almost not quite 100 years now, but almost 100 years. We've been detecting these basically you gotta put these detectors that can detect S and P waves all over the planet, And anyhow, so now, of course, it's all over the planet. At first, it wasn't. It took a while before we could get a clear picture of what was going on. All right, so the S and P waves are created, and they propagate outward from a location somewhere on the Earth. And if you have a detector, let's say let's say right here. Okay, this is a good place to start with. And so you get both an S and a P wave right here. All right, maybe a little bit further along. There is let's say there's another detector, let's say right here, okay? And then you're going to get an S and a P wave at a little bit later time, right? Because of course it takes, since this detector is closer to the original earthquake, this is called, and where the original earthquake is called the epicenter of the earthquake, right? So these waves propagate outward. Closer say like this detector would get these waves very quickly. All right, so they don't travel exactly at the same speeds, but that's not really important to our story. The thing that's important is you're creating both S and P waves. All right, and so detectors over here would detect S and P waves. Detector right here. So but there's a cone shaped. So imagine like if anything on the inside of this, okay, so where I'm mapping or showing you with the cursor here, anything inside of this cone would be what you'd only see P waves, right? And so you don't find any. So all from this particular earthquake, okay, so that's what I'm talking about. From this one earthquake on this side of the planet, in this cone-shaped area, you're only going to get P waves. And the reason for that, and it took a long time for people to figure this out, by the way. This was not really obvious at first. So people study these S and P waves, and we're going to look at that at here. There's the P waves, and here's the S waves. All right. So now the S waves, they shake back and forth like this. Like the wave travels along in a certain direction. But the S waves wave back and forth perpendicular to that direction. With P waves, which the thing that waves is waving in the same direction that the wave is traveling. So these are two completely different types of waves. All right. So anyhow, the P waves, as it was discovered, we artificially created, well, not artificial, we created S and P waves, and we found that P waves, which remember oscillate back and forth in the same direction that they travel, can pass through solid material, of course, and also liquid material. They pass right through liquid. But S waves, when they'll pass through solid, but as soon as they encounter liquid, they stop. They can't pass through liquid, right? And so because they can't pass through liquid, we know that the interior of the Earth has a liquid core, right? So there's an outer core of the Earth, right? So I didn't really go into this too much yet. There's a crust. Right, there's a thin crust of the Earth, right? So that's the part we live on, and then there's the mantle, which is solid, and then you come to the core. There's an outer core, which is known as the liquid. It's a liquid core because S waves can't pass through it, and then of course there's an actual solid core, and the core of the planet is made But both of these, the solid and the liquid, is made of iron and nickel. All right, so right, so anyhow, that's just one earthquake, right? So you just imagine, right, any given day, there could be hundreds and hundreds of earthquakes, and I'm talking about really tiny little earthquakes, not these gigantic ones, but there's little tiny earthquakes all over the planet constantly, and so these S and P waves are constantly traveling outward. And so we've mapped this, we map these all the time. And so we have a really good picture, if you will, of what's going on inside the Earth. I mean, we know exactly how big this liquid core is, and how big. And now you might wonder, okay, how do we know there's a solid core here? Okay, so now what happens with the P waves, and it's not showing you this. Well, actually, it is showing you a little bit of it. Okay, so here's what happens with the P waves, right? When the P waves travel through the liquid material, okay, so they're easily able to go through that. We already know that they can travel through solids, but when they travel through a solid material, they will actually bend. You know how just like when light travels through glass, or light travels through water. That's called refraction. It bends, and so the P waves will bend, and that's how we know this size of this the solid inner core, which is made mostly of iron, but iron and nickel. All right, so those two elements make up the core of the Earth. All right, so that, I mean, there's a whole study if you're really interested in that kind of thing. There's a whole bunch of geological. It's geology actually. That's part of geology is studying the S and P waves. All right, so anyhow, that's how we know. And again, it's not from a single earthquake. There are literally thousands. We have hundreds of thousands, perhaps. I don't even know how many we have. So we have this data from all over the planet for many decades, and so we have formed this picture of what's going on in the interior of the Earth. All right, this did not happen overnight. It took a long time for humanity to figure this out. All right, so again, this is so these are the P waves, also known as primary waves, are actually compression waves. I don't know how much of the wave stuff I need to get into. That might be a little bit too much physics, but so these waves, the P waves, all right. I'll use another term here. This comes from physics. These are longitudinal, right? So when the wave travels in the same direction, when the thing that's waving, right? It's like imagine this is a spring, and there's a compression in the spring, and that compression propagates along, in the same direction. All right, it's that's the thing that's waving, is this, these springs are a little bit closer to each other, and that passes along from springs to spring. All right, so that's a longitudinal wave. These waves right here, the S waves, are also known as transverse waves. So transverse just means perpendicular. So the thing that they wave perpendicular to the direction that they're traveling. The longitudinal waves they wave in the direction that they're traveling. All right, so and in fact that's why the S waves can't travel through liquid, right? If the wave's going perpendicular to itself and it passes through liquid, the wave can't bounce back, as it were. All right, anyhow. Let's see. So this is This is the same picture.